So I want to tell you a little story to introduce the next speaker. So like 100 years ago, the group of physicists from Austria, Schrödinger, Pauli, Ehrenfest, were developing the foundations of quantum mechanics. And things began to get complicated when they started having many body problems. There were a lot of symmetries involved, and people started to suggest group theory would be a way to organize this. And the Austrians were very resistant to this. And the three of them started to refer to the Gruppenpest, so the plague of group theory that was infecting quantum mechanics. They saw it as pure formalism that didn't give any physical intuition into the actual state of things, and they were resistant to learning the group theory to follow these new developments that were coming out from people like von Neumann and Winger and Weil. And so the group theory, became useful, and in particular representation theory turned out to be very useful in quantum mechanics. So the next speaker is a physicist. This is Alexander Stottmeister from Hanover. And he's going to tell us how physicists now are still interested in group theory, in quantum mechanics, quantum field theories, and in particular groups like Thompson's group, how this figures into modern physics.
Well, okay. Thanks, Chris, for the kind introduction and already mentioning some of the motivations. So I obviously must admit that this is a kind of different audience than I'm usually talking to. So I try to just introduce some of the ideas which I'm working on and which some people are interested in, and how this might be related to, I think the question that Chris posed to me, why physicists might be interested in Thompson groups or other infinite discrete groups. And well, maybe to give like a simple but not so enlightening answer is that, well, physicists like their approximations. So if you want to describe physical systems, yes, I try to, okay. So physicists like their approximations in describing quantum systems or even classical systems, and especially when they are dealing with systems that exhibit like infinitely many or continuously many degrees of freedom. And in particularly when we do such approximations, we would like to keep a lot of the symmetries around that are assumed to be there in some, say, continuous theory. And well, to clarify that a bit more, so some of the most, let's say, interesting or subtle phenomena are described usually by what is called quantum field theory, although you might say that quantum field theory from a mathematical point of view is kind of still under development. But one thing we kind of rely on typically is that we can approximate quantum field theory in terms of like finite or discrete systems, which are then usually handled in the context of quantum mechanics. And in this approximation procedure, we would like to retain some of the symmetries. For example, in quantum field theory, usually quantum field theory deals with relativistic systems. So you want that your system in the end has Poincare symmetry, so space-time translations and spatial rotations, and also what people call boosts, so transformations related to change of the velocity of the system. And there's even more specific type of quantum field theory, which are so-called conformal field theories. And they relate to like the second thing in the title, so the renormalization group, which I will explain in a bit. And these conformal symmetries mean that you have additional symmetries under scale transformations of your system. Or more generally, then if you combine this with some physicist reasoning, you should have invariants under conformal symmetries of the system. And this is particularly interesting in, let's say, low dimensions, so 1+1 dimensions or 2 dimensions, because in that case, you basically can boil it down to something like diffeomorphism symmetry, and that's where the connection, for example, to the Thompson group appears. Okay, and so in this sense, why should we be interested in something like the Thompson group? Well, there was the idea in that case by Vaughan Jones, maybe you can use the Thompson group as a discrete approximation to the conformal symmetry. And then if you let it act in a certain sensible way on a limiting space, maybe you can use it to actually approximate conformal symmetries of a theory that is defined via a certain limit construction. And to understand this limit construction a bit better, or at least the intuition behind it, I want to explain to you what I mean by this renormalization group. So first of all, I should say it's not a group. Yeah? So it's just a name that stuck in a sense. Yeah? So it's more like a semi-group. And what it refers to is the idea that, that's why it's related to conformal field theory, is that you want to understand how a physical system behaves when you change the scale of observation. So you look at it at a coarse resolution and at a fine resolution, and you want to understand how this is linked. Yeah? Because in the end, the system should be some unique whole thing, at least in many people's mind. Yeah? And so there should be a relation, and the renormalization group is essentially that object that should relate the different resolution scales. Yeah? And that's kind of what is you want depicted in this picture here. So what you think about is you look at your system at a scale n. So what we mean by scale n is essentially that it should be something like a log scale of some reference length scale epsilon, of some length scale epsilon to your reference scale epsilon 0. And at this scale n, your possible physical theories, they should form some kind of mathematical space, yeah? So to be specified further on. But what is typical is that, for example, each point at the scale in this plane I draw here would be like the, for example, Hamiltonian that governs the dynamics of a given system. Yeah? If you think about a quantum system, you have a Hilbert space. On that, you have a self-adjoint operator, which is the Hamiltonian. That gives you some dynamics by exponentiating it. Yeah? And the states of the system are these vectors in this Hilbert space. And usually your Hamiltonian depends on some coupling constants, which are your kind of experimental parameters that determine the dynamics. And so what you want to think about is now like the space of all these Hamiltonians, yeah, that at a certain scale that make up all the possible dynamics. And you want to understand how is this space at this scale related to a space of possible dynamics when you when you go to a higher resolution. Yeah? So going up in n means you go to a higher resolution, minus log. Sorry. And so you want to think of this in a sense as a dynamical system. Yeah? So there should be an operation, and that's the renormalization group, that brings points from here to here. And to define the continuum theory, what you want to do is you want to basically follow this flow of the renormalization group or the semi-group to its endpoints. Yeah? And that was essentially, like in this general context, that was the idea of Wilson and Kadanoff. And particularly important objects in this picture are critical points, and critical points are those which are essentially lead you to fixed points of under this are fixed points under this renormalization group transformation. Huh? Yes.
So that's mean that you go in the left a smaller scale,
Yeah, that depends a bit on whether you talk about the states or the observables. So you would, if you talk about states, then you would coarse grade. So you go from a lot of from states on a fine scale to one on a coarse scale. If you talk about it in terms of observable quantities, then it's actually the other way around, because the observable are essentially operational duals to states. So you will reverse the arrows. And so this picture here should be the reversed direction. So you talk about observable quantities. Yeah? So yeah, your Hamiltonian, for example, that would be typically associated with the energy observable, and you follow that in the other direction. But those two things are essentially equivalent. Now, so what I want to get at here is why should be especially interested in these fixed points? Well, the idea is that kind of non-trivial continuum theories, they should live close to such fixed points of the theory, in the sense that typically what will happen if you iterate An RG transformation is that you either are at a fixed point, then you go to this fixed point under the flow, or it diverges away from it. So that's like the typical observation. I mean, maybe there could be other behavior, but that's what you observe. And then the idea is now, okay, to end up with something non-trivial, in the end, what we should do is we should end up somewhere close. So in the continuum, the picture should be that this is kind of a locus of where various unstable manifolds meet. And we want to define continuum field theories by something that is in the vicinity here. So what we should do is we should actually rescale these coupling constants when we do the renormalization group transformation, and that will lead us essentially, I mean, that means that we move these trajectories which are diverging from the fixed point is eventually closer to here. And if that has a sensible limit, that would be a continuum field theory. So that's kind of the overall picture. And why should that be the case? Well, yeah, the thing is that if you're at a fixed point or a conformal field theory, that should be something which is scale invariant. So essentially correlations of certain observable quantities in your system, they have infinite correlation length. Yeah? So if you have a certain state, say it's a probability measure in the classical case, or in the quantum case, you have a state on a von Neumann algebra, for example, and you take two observables, which are operators associated with some location in space, and you look at the correlation functions of these two things, then at each scale, this is measured in terms of the length scale of the system at that scale. So, but the renormalization group typically leads to the fact that these correlations wash out, so you have to rescale the coupling constants to stay close to something which has non-vanishing correlation functions. Yeah.
If you think of the critical points at different scales,
the point is, I mean, it depends a bit on the picture, but the idea is that you go from this point to this point here. Now you rescale all quantities back to here, and under this rescaling and constraints, that is a fixed point of this transformation. That's a critical point.
Okay,
I will try to make an example. But that's kind of the overall idea. And well, maybe now I can tell you a bit how this can be explicitly realized. So like maybe the most well-known model where this kind of intuition should hold and has been proved to hold to a large extent is when your discrete model, or your model at scale n, is given by a classical Ising model, yeah, on a 2D square lattice. And in that case, the critical point would correspond to the critical temperature of this model. And the idea is that under renormalization group transformations at this critical point, you should actually obtain some conformal field theory. And that's kind of well understood by now that this actually works. And what I want to talk about today, or the example I want to present, is essentially the quantum version of this model. So let's try to make this quite concrete. So what we want to talk about is we want to encode what are these quantum systems in that case at each scale. So what we start with is some C-star algebra A at scale n, some Hilbert space on which this algebra acts, and some Hamiltonian that governs the effective dynamics on this system. So this is like a sequence effective quantum systems. And what so the picture you should have in mind is something like, okay, you have like a square grid, and at each vertex, it's some C-star algebra. Let's say it's just, it could be, for example, something like d-dimensional complex matrices, and the total algebra of the system, so AN is something like this, and well, you represent it on its natural Hilbert space, and then the Hamiltonian have that. Some self-adjoint element of this algebra. Now, because you do this for various scales, so at a refined scale, would basically have the same picture, but now with an increased number of lattice sites. And as I said before, so if I only had the sequence of discrete quantum systems, that's kind of not, I mean, that's not enough to do sensible physics with it. So what I want is also a realization of the renormalization group, which should essentially give me some link between these systems here. So this renormalization group should link the systems at different n. And well, coming back to this first question, whether we do coarse graining or fine graining, if you want, or refining. If you look in the physics literature, then typically one starts from a coarse graining procedure, which in this context means you think about states of the physical system, which are now just states on this C-star algebra. So an expectation function is normalized. And if everything is finite dimensional, they are typically represented by trace class operators with trace 1. So and a typical state one starts from is the so-called canonical density matrix of the Hamiltonian that governs your dynamics, because that's something like the probability, like the Gibbs measure associated to Hamiltonian in the classical picture, and something like this. So that should be an element in this case of, let's say, the bound this operator algebraic languages should be in the pre-dual of the bounded operators of your system Hilbert space. And the coarse graining operation you want now is a map goes from a fine scale to a coarse scale. So it should be linking these states. And with the condition that m is smaller than n. And of course, we want some properties for this map. So it should not be just an arbitrary mapping between these two spaces, but we want it to be completely positive. Be trace preserving. And Sorry. Here should be the pre-dual space, so this, the space of which B of H is the dual. In that case, it's, yeah. So in this case, it's just the trace class operators. And you want this composition property, which is where this name renormalization group comes from. So basically saying, okay, put correctly. So basically saying that you have this possibility to do this coarse graining procedure in various steps. And of course, I mean, this could be satisfied if we just talk about discrete number of steps we are imposing. We just specify the step for one, going between systems that are separated by one step, and then we iterate this mapping. Okay, and then these other two properties basically mean, okay, trace preserving, that these operators which we are looking at, they should have trace one if they are a state, which means that essentially doing nothing to your system has a probability of 1. And so demanding trace, that the trace preserved under this thing means that the probabilistic interpretation of your system, of your description is still valid even after coarse graining, and the complete positivity means that essentially you can tensorize your system with a lot of identities, meaning you can embed it into a larger system trivially and still do the procedures. So it's a kind of, localization property. So you can always consider your system you're looking at as some subsystem of something larger, and then it should be compatible with this idea. And why should we want that? Because, well, in the end, I mean, if we really want to talk about the quantum field theory on, let's say, a non-compact space, or on all of space-time, we should be able to basically start from this renormalization group procedure in a finite volume and then go to some infinite volume limit. And so to have some compatibility with the infinite volume limit, we want this complete positivity. And now, well, since we do not really want to do this in a formalism focused on states, but in terms of operator algebras, we can essentially dualize this. So these maps, in the sense that instead we are looking now at mappings between the algebras which encode the observables of your system. So for the same. And in that case, that means that, again, these alpha maps should be completely positive. Now, the trace preserving translates into being a unital map. So if your C-star algebra is unital or contains a unit, this unit should be preserved, which is, again, this idea of preserving the probabilistic interpretation, and the composition just now goes in the other direction. Okay. And once we are given this, we can now formulate what this renormalization group procedure should actually do. So we basically need this. So as a setup, we need this initial sequence of quantum systems, C-star algebra, your basic observables, a Hilbert space on which they act, and some dynamics. And what we also need is for each scale, we need a fixed state, because that will be essentially the thing that will describe this fixed point here. Instead of, I mean, initially I said, okay, you might think about each point in these planes as some Hamiltonian, but instead of, which would be the idea, having this object here, but from the Hamiltonian, you typically also canonically associated to it some states. And the formalism, which is kind of easier to handle, is instead of working directly with the Hamiltonian, because it's hard to give them a nice structure of, let's say, a Banach space or whatever. It's easier to work with states, because if we just look at states of some C-star algebra, we already have some kind of compact space in the weak star topology. So the additional data. Each of these objects is a state on AN. And, well, in the classical setting, you would give yourself a probability measure. That's the idea. And now the renormalization group flow, so these lines which we are here constructing, that just the following. So we look at a state at a fixed scale M, and then we, and then we consider this sequence. Yeah, so means, so you fix the scale n, and what you do is where you move in your initial sequence up in the scale and pull it down back to that scale. That gives you a sequence of states on the fixed scale you're looking at. And this is the G flow equation. And the main question is now, when you want to construct a continuum theory, is it possible to find the limit point of this sequence? I mean, does this even have a sequence? And I mean, of course, this state might depend on some parameters, these coupling constants, which I mentioned at the beginning. So it's a kind of conditional statement whether it converges in the sense, is there a choice of such coupling constants internal to these states such that this sequence converges as a sequence in this parameter here? So you could say, okay, does this limit exist for some choice of initial states? And of course, what is now sense easier than in this Hamiltonian picture. So since we're talking about states, this is always a sequence in a compact space, because we're just fixing this M and look at it as the limit in N. So it's a sequence in the weak, so we can at least know that there are some weak star limit points for this thing. The more physically, the more important question would be, are there actually interesting limit points? And the interesting limit points should be those correspond to these fixed points here. So what we would actually like to do is, okay, we want to additionally look at discretized symmetries that act on these observables here, such that possibly existent limit point of the sequence of states actually has conformal symmetry. So, and in the case of, let's say, one-dimensional quantum systems, which would morally correspond to two-dimensional classical systems, that would mean that we want a limit point here such that the induced representation of the limit state seen as a state on the inductive limit of these algebras here. You do the GNS construction, so you induce a Hilbert space representation with respect to the limit state here, that actually carries a representation of the diffeomorphism group of S1. We look at this limit algebra, the inductive limit of the ANs with respect to these maps here. I mean, that inductive limit, at least as a Banach space, will exist under quite general conditions. It will also be a C-star algebra, provided these maps, for example, here are asymptotically multiplicative as maps on the algebra as well. Now, what you now also have is this limiting state. So let's call this one omega m infinity if it exists. And then you can form the projective limit of this thing here, which always exists as long as this limit exists. Yeah? So it's already, so if you can show that this limit exists, then this is well defined as a projective limit on this inductive C-star limit algebra. And now we look at the NS representation of this pair, meaning that you construct a Hilbert space by basically forming an inner product completion of A infinity, where the inner product is given in this form. Yeah? So we have the classes of two elements. If you form the inner product, then it's just this one. So that gives you a natural Hilbert space structure of quotient on a quotient of A infinity, but by the left ideal with respect to this state. Okay, so this is now the continuum limit or the limit quantum system, because that outputs essentially a certain vector, a representation of this algebra in the Hilbert space on which this representation acts. Now the question is there finally let's say in this case, we put periodic boundary conditions. It should be some action of the diffeomorphisms on the circle. And the idea is in that case, okay, why would you expect something like this? Because in one dimension, your lattices would basically be just partitions. You put periodic boundary conditions, you look at partitions of the unit circle. So this algebra basically describes a quantum system living on finer and finer partitions of the unit circle. And in the end, this thing here should define a theory that lives on the circle on which you actually then have an action of the diffeomorphism group. And that's kind of where this idea with the Thompson group comes in now, because if you think of these partitions as standard dyadic partitions, so you just fix the length of your circle to 1, essentially, and only do refinements by powers of 2, so you always insert like new vertices in each step at the midpoints of intervals. Then, of course, on the inductive system over something like this, you would get an action of the Thompson group, basically by just operating on the index set of that partition. And in this case, it's most natural to look at this Thompson group T instead of just F. And well, that was kind of the observation of A. Jones, that you can ask now the question, okay, if I have an action of t on this inductive limit, so this means that say I choose my lattice under n, something like this is fixed to 1, and each epsilon n, something like this, then I have a natural action of the Thompson group T on this. And I think it was in 14. There's a natural action of t on A infinity on this limit algebra, provided that these one-step maps are closed. The idea is basically you get such a natural representation on this limiting object here, provided these maps here are essentially constructed from representations of a simple binary tree. And why is that so? Because probably better known to you, because if I look at an element, say in F, then I can represent it essentially as a fraction of two trees, T1 and T2. So a typical example would be, okay, this one. So we have this on top, and then maybe, so that would correspond to an element of the Thompson group, because each of these trees describes a standard dyadic partition. And this fraction basically tells you how to map these elements of this dyadic partition to one another. And if you do it based on these trees, they also have this property that you have slopes which are powers of 2. And now if you think of the inductive limit, so if this A infinity is also essentially, if an element in here is essentially something which is labeled by some tree, and this, which means by a dyadic partition which corresponds to such a lattice, and you get an action of the Thompson group on elements or on a dense set of elements inside here by essentially acting on this label here. You only get it on A infinity, of course, because the Thompson group action might change the labeling, but in the limit that thing is well defined. Now, well, here we said, okay, for a CFT, we actually want to have an action of the diffeomorphism group within this GNS representation. So we think of a unitary representation of the diffeomorphism group. So the question would be, is the limit here such that the action you get naturally on the algebra also induces an action on the limit space constructed on this data. And well, there is a theorem by Jones for a certain spin chain model where it actually doesn't work and it fails like in a kind of spectacular way that not even the rotations, so if you extend this f to t by also including dyadic rotations, that not even the dyadic rotations are implemented in a sensible way. But, okay, maybe there's hope. So you could think, okay, maybe this is just due to the fact that you're asking too much with these unitary representations. Can it actually work on the algebra? So, I mean, we can construct certain models where you also have this diffeomorphism group action on the algebra itself. And then you could ask, okay, maybe I cannot compare the unitary actions of the Thompson group and the diffeomorphism group, but at least the automorphic action on the limiting algebra. But yeah, so far looks like that in interesting models this is also not really possible. And the problem there is of a different kind in a sense, because in the case of the unitary actions, the problem is that the Thompson group elements are not even implemented on the Hilbert space. So you do not even get a unitary action in that case. But on the algebra, the problem is due to the fact that because you only have these slopes of powers of 2, you're not able to approximate a diffeomorphism in a topology that is not just a subtopology. Maybe can conclude with the statement that for us it would be interesting, so if there are other like natural candidates than the Thompson group. So the Thompson group in a sense looks a bit too coarse to do these approximations for CFTs. I mean, although in this model, I cannot really now introduce it, but in this model where we have the action on A infinity, looks like if we are allowed to, for example, extend, or if we would choose, let's say, all piecewise linear transformations between dyadic partitions where we also include other slopes, not only powers of 2, then the approximation works. In that case, it's really only due to the fact that we only have powers of 2 and in this sense are not dense enough in the space of derivatives. So yeah, I think the thing would be for at least for these CFTs would be more natural to look at other discrete groups which are a bit denser, if you want. I mean, they are not really dense in the diffeomorphisms, but get closer to it. And but on the other hand, what maybe as another comment, it's nice. So the work which I did with Arnaud Brothier on this was a different kind of model where basically these algebras here in these discrete models, they are not sitting at the vertices of the lattices, but on the links, and are valued in, let's say, transformation group C-star algebras for a compact Lie group. And in that case, these models are related to what is called a discrete gauge theory, so lattice gauge theory. And in that case, we found that at least you can construct nice actions of the Thompson groups, which are outer on certain von Neumann algebras from this thing. So let me stop with this.